Welcome to the Canadian Tech Journey. Okay, so in this one, let's continue and start talking about some more RF stuff. This time it's going to be RF components. We have already covered. Okay, so in this one, we're going to talk about more RF stuff. This time it's going to be RF components. So far, we have already covered RF characteristics and RF behaviors. Now, this time we're going to talk about RF components, which really means is the system is made up of what components. So when I dive into this and I start looking into what is my system made of, it is basically made up of a transmitter, an IR, and an antenna. Now, transmitter is a device in which I'm going to put my data in, and it's going to take that and convert into actual signals. IR is where I'm going to kind of add that gain, intentional radiator, where I'm going to add that gain, which is an active gain. And then it's going to the antenna where it's going to add passive gain. Again, if you remember the last time conversation we had, IR is more going to be active gain, which really means is I'm blowing air into a balloon to make it bigger. When I'm starting to focus energy in a certain way, that's where the antenna comes in, which is passive. Sums of all the losses plus the gains gives me what my signal is going to look like. So if I go to my next slide, which actually is a very good diagram, which is I've taken from the CWNA study guide, which is written by David and David. If you are on that journey of CWNA, I would highly recommend this book. I till date use this book as a reference. So again, if you're looking back at one of those diagrams that you're seeing on the slide, it's like data is sent, goes into a transmitter, passes through the cable, and then goes through the antenna. So what's coming out of the antenna is really EIRP and what's gone there before. So the FCC is monitoring for this and this. So you are having a limit on how much power you can put in, and you also have a limit of what kind of high gain antenna can you put in. Once it gets converted into radio waves, then you have a receiving system that converts that radio waves back, and then finally you get the ones and zeros that you're looking for. Now the next few slides that you'll see here are just talking about each of them. So transmitter is going to be the component that takes that signal and creates into RF. It basically modulates that signal, and again we have spoken about all that in the last episodes. Antenna is a system that is going to be adding passive gain. The main idea of antenna is to do passive gain, as I mentioned, and also it does not just help with transmitting, but at the same time is also able to help with receiving. Receiver is the final component. Once you send that RF, then the receiver needs a similar system so I can receive those RFs, start changing them back into zeros and ones, and start to make sense of the data that has been sent to me. Okay. Intentional radiator, again, the FCC is monitoring our IR in order to make sure that how much power am I allowed to generate, and at the same time after the antenna it's also looking at EIRP, which is coming out of the system, which means coming out of the antenna. So again, anything before entering the antenna is IR, anything that is coming outside the antenna on the other side is going to be EIRP. That's the easiest way to remember that. So these are the three, the components that we see. So these are the components that we see from a perspective of RF components. So you saw that there is a transmitter, then there's a cables which have some loss that are connecting everything. Then you have an IR, then you have an antenna, then you are looking at an EIRP. Okay, so those are the few things. Again, very high level. If you understand those things, then you understand a system that's going to be used in Wi-Fi. Okay. Now RF math is important is because we need to understand that how does the signals get measured, right? So these are units of power. We're going to be focusing more on milliwatt here, and dBm is what usually you measure Wi-Fi signals in. Watt is signal of power, but again, because our power that we work with is very small, as I mentioned already, that's why we're using milliwatt, which is 1,000 of a watt, right? And it's an absolute measurement, which means it is right. It's exactly what it is, right? It's not a comparison or something like that to anything. So if somebody says this person is weighing 70 kilos, that's an absolute value that it is 70 kilos, right? That's what basically that means. Now decibel is a comparison. That's why it's called a unit of comparison if it's dB. This you'll see more in the next episode where we talk about antennas. So we have an isotropic radiator, which means it's an ideal antenna which pretty much looks like a ball, that it's able to radiate equally in all directions. Now it's ideal, I would say theoretical. In real world that's not going to happen. So the difference between typical isotropic radiator and my antenna is measured in dBi. That what's the difference, right? Similarly it's similar to manage with the dipole antenna. Now like anything else, in life. Something gets more commonly used than the other. These are ways of measuring antenna, I would say, gain. But dBi is something which is more commonly used. So when you look at data sheets of an antennas, you'll usually see dBi. Sometimes you might see dBd, but it's rarely the case from what I have seen from my experience. Okay. Watt, as I mentioned, it's already it's just a basic power unit of power, which I mentioned already. It's part of the slides, so in case anybody is kind of following through from a perspective of learning, provided them. Milliwatt, as I said, this is what we used because the levels in Wi-Fi are typically very low, between 1 milliwatt to 100 milliwatt. Outdoor sometimes can go a little higher depending on, again, the regulation set by FCC. So that's why it's milliwatt is one, as I said, 1000 of watt. Okay. dB, as I mentioned, it is a unit of comparison when you're trying to measure the change in power. You're not so if a signal comes out of a particular device, and then at this place where I'm receiving it, how much has it dropped or increased is dB, right? It's not an absolute value. Again, it's a unit of comparison. The reason we use decibel is because, see, think about this. When I'm trying to get a signal, if somebody tells me that you're getting, now these two signals, milliwatt and dBm, are both absolute, means actual values. But if I have to say that, okay, I'm getting 0.0000001 milliwatt versus, oh, I'm getting minus 80, it's much easier to talk about when I say I'm getting minus 80, right? So that's the reason why we use dBm more and not milliwatt, especially when we're receiving, because once you put a power into an AP, because of the free space loss, remember the graph I showed you in the last episode, you see a drop, quick drop, and then soon the values are going to go in decimals, which are hard to say that, okay, this is point so and so milliwatt. But if you use a minus 80 or a minus 67 dBm, which is much easier number to work with and to talk about, right? Again, as I said, dBi, explain that what that is. So it's a comparison with an antenna. And then again, similarly, we have dBd, which is dipole. Okay, so just giving you that. dBm, again, as I said, is an absolute measurement, which is used mostly. So again, all the power that I'm going to get is, if I'm using any of the Wi-Fi scanner devices today, like Wi-Fi Analyzer, a lot of free apps you can download on your Android and Apple phones, I think has a couple of options as well, where you want to see that what's my signal at this point. So that signal is usually shown in dBm. Now I can actually show mine here as well. So I have another tool that I use. So if you look at my signal strength here, it's in dBm, right? So it's much easier to say that, okay, I'm getting a minus 69, minus 61, minus 81 versus saying I'm getting something in decimals. Now you can go to an online calculator and get something like this here, where I can say in dBm I was getting minus 67. Can you convert that? Now, is it easy for me to say I'm getting minus 67, or is it easy for me to say 0.0000? So I hope you get the point here, right? So it's just that it's much easier to work with when you're working with these other numbers, which are in dBm, and that's the reason we started to use decimals. So hopefully I'll be able to convince you that why you should use dBm versus standard milliwatt here. Okay. And then because you want to compare, or I would rather say, and then you want to convert from one form to another, there are certain rules that you can use. So these are just some of the summaries that, okay, but the easiest way or the best explanation I have ever seen of this is actually, there was a video from Keith that he explained a certain number from this side to that side, where I'm saying this side to that side, which really means from dBm to milliwatt, right? So I would highly encourage you go ahead and watch that video, but I'll go ahead and put this into the notes as well, so you can kind of take a look at it, okay? And the idea that he walks through is you pretty much have like a table that you can make, right? From dB to normal, right? Normal means milliwatt. So a plus becomes, the way he explains that is, a plus becomes, you just change the sign and it becomes times, minus becomes divide, 10 stays 10, and 3 becomes 2. As long as you have that table in mind, most numbers that you'll get in any exam, especially the CWNA exam, you will be able to make those conversions pretty straightforward, right? So let's say I had a number that I had to convert, it would be easily converted. For example, if I had, let's say I want to make sure I have 30 dBm, for example, right? So how do I convert that into a normal? I'm taking the simplest more example, so it's 10 plus 3, right? That's how I can make 13. So 10 remains 10, plus becomes time, 3 becomes 2. So that's 200 milliwatt. Just an example. You can look into some more examples that Keith walks through in his video, and I think that's the best explanation, as I mentioned, that I have found ever. Highly recommend that you go over that video and get some more practice if you wish to, right? Another concept we're going to talk about is signal to noise ratio, which really means is there's a difference between the actual signal and then the background noise, which is really thermal noise at this point. Generally speaking, in any given room like where I am right now, if you measure natural noise using a spectrum analyzer, you'll see somewhere about minus 93 to minus 94, depending on what your signal is. Let's say if it's minus 63, so I'm looking at about a 30 dB SNR. Again, if you have 30 and above, generally that's very good, where I'm able to kind of differentiate between a good signal and a bad signal, and I don't have a noise. Now, giving you an example is, let's say if I was sitting right here and having a chat with my friend, right? There's no noise here, I can definitely hear him. But now let's say if he opens the door and goes out to get a drink for himself, and from there he's yelling, "Do you need one drink as well?" Far, now the signal strength has actually dropped that I'm going to hear him at. I might not hear properly, or I might hear it. And now let's say if there was outside, somebody was watching TV at a high volume, now that's mixing with his voice. Now that noise floor has stayed the same, but other noise has added the noise to go up. The signal is low, so the SNR is lower and lower. So now my chances of understanding clearly what he was trying to say when he was in the room versus outside with the TV on changes. That's the impact of SNR outside, right? So when you have a good SNR, you are easily able to detect the signal and understand what the person is trying to say. Okay, so that also in line sets with your higher data rates. You're able to send data quickly because you're able to understand quickly. But if your easiest way to imagine this is it's the signal strength, is the number of bars that you see on your phone or your link budget. Again, if you have a point-to-point connection, sum of all the gains versus sum of all the losses is what the link budget is. Usually you want to have a certain link budget, is because let's say if you want to have a bridge give you a certain output, like I need to make sure that it's able to give me a certain amount of throughput, then you need to understand that my SNR and my gains should be to a certain point where I'm able to make sure that every time my data rate is such so that I get enough throughput from that wireless system that I'm putting in place, right? Now, easy way to remember this is you have a transmitter, right? So you put a certain power in, and then it goes through all these cables, lightning arresters, and antenna. So you have these cable losses and the components connector, and then you have an antenna. Then suddenly you get that. So this is where your IR is, and then suddenly you get a passive gain from the antenna. It peaks up, and this graph, if you remember, should be exactly the same as your free space loss that you see. Go down again. And as I mentioned with you, the antenna not only helps in sending but also in receiving. So can you see a peak up, then you see a drop down again from all the cable losses, and that's your receive power. So again, there will be a gap between transmit power and receiver power. But then if you say it goes up and down, so whenever you see an antenna, it goes up because it has that gain. Whenever it passes through free space loss or any of the cables, you see a drop. Okay. Fade margin is just that that bridge that I had. So let's say if I wanted to have a certain sort of throughput that I needed. So if I needed certain thing, I will buffer it up to something. Okay, I should get 10 to 25 dB more, so I can make sure if my environment changes. If you remember the last episode, we spoke about when you have an outdoor bridge, refraction or things might have my signal go somewhere up because of the weather has changed, it's cloudy and stuff. So it's just covering up for those things. So that's basically your fade margin. Okay. So that's it. I guess that's the only thing I had to cover in this specific episode. And again, the goal is just to keep them all short and hopefully give you enough information in quick 10-12 minutes videos. All the best. See you in the next one. And that concludes another insightful journey through the world of technology with Canadian Tech Journey. I hope you've gained valuable insights and a deeper understanding. Remember, the learning doesn't stop here. Keep exploring, keep cautioning, and keep learning. Feel free to subscribe to the channel for more exciting content and updates. Thanks for joining me on the Canadian Tech Journey. Until next time, keep learning and stay curious. See you in the next adventure.